Hi everyone, Charles here for ML New Papers. Long time since we did a research paper video on this channel, and the paper we are going to see today is nothing short of amazing. We will see how a simple coin betting game can help us to optimize the parameters of a neural network. As a disclaimer, this video is on the more technical end of the channel. All the research papers that I present here are among the best that modern machine learning research has to offer, and understanding even part of them puts you on a professional or close to professional level. That also means that if you are newer to the field, understanding them is a challenge per se, but great rewards only come after great challenges. Today's paper is titled Better Than KL PAC-Bayes Bounds. It has been written by Ilya Kuzborskij, Kwangsung Jun, Yulian Wu, Kyung-Sok Jung, and Francesco Orabona, and it appeared last year 2024 at a prestigious conference on learning theory. In today's video, we will first see a quick introduction to coin betting and to the world of PAC-Bayes. Then we will see a new surprising PAC-Bayes bound introduced in this paper and how the authors used coin betting to obtain it, notably going through their short yet insightful proof. Before we start, that would be so great if you could give this video a thumbs up, subscribe and hit the bell icon to get notified of the next video. That's completely free for you and that really helps the channel. Thank you so much. Finally, I want to mention that we have received on this channel one of the authors of this paper and someone who is for me one of the greatest machine learning researchers in the world, Francesco Orabona. Francesco has given us a very inspiring interview on his journey from playing the game of Lego to doing research in online learning, explaining the principles and challenges of the field. If you haven't watched it yet, make sure to check it out at the end of this video. The link will be in the description box down below. Let's jump into the paper now. The coin betting game. Coin betting belongs to the huge family of online learning problems where you make a decision, receive an observation, make a decision, receive an observation, and so on sequentially. Here we do not make any assumption on the observations. For example, they could as well be chosen by your worst enemy. And therefore, online learning results and methods can be applied to the more specific setting of standard machine learning, which assumes that the observations are independently generated from a probability distribution. In coin betting, you have an initial wealth W0 equal to 1. At every round I from 1 to n, you bet the signed fraction beta I of your current wealth Wi minus 1. Your friend then reveals the outcome of the coin, delta I is equal to plus minus 1. And your wealth changes by delta I, beta I, Wi minus 1, which is an increase if beta I and delta I have the same sign, and a decrease otherwise. You want to find a strategy beta 1, beta 2, beta n to maximize your wealth Wn at the end of the game, which, following the above formula, writes as this. And then we can apply the same formula to Wn minus 1, which writes as this. And so on, giving the following formula for your final wealth Wn. As Francesco explained in his interview here in ML New Papers, since the observations delta I are arbitrarily chosen by your friend, there is no way in the world you can forecast them. So instead, your objective is to perform almost as well as the best fixed constant predictor beta, which achieves the total wealth Wn star, for which we know a lower bound. Our objective can then be expressed as minimizing the regret compared to Wn star, formally defined as the quotient Wn star over your final wealth Wn. Now the good thing is, some researchers have extensively studied this problem before us. They have generalized it to the case of a continuous coin delta I between minus 1 and plus 1, and found a coin betting algorithm whose regret is always lower than square root of 2n plus 1. And we'll see later that this innocent result has some surprising applications to PAC-Bayes bounds. A short introduction to the world of PAC-Bayes. I will make a very short introduction to PAC-Bayes bounds just for the purpose of today's paper. But if you want to know more, there is a phenomenal book on the topic. This one, it's called User-Friendly Introduction to PAC-Bayes Bounds, and it has been written by one of the behemoths of the field, Pierre. That's a fantastic read. Strongly recommended. The references of the book will be in the description box down below. Take a parametric model. For example, a neural network N, which depends on the parameter theta. You want to find theta such that your neural net n of theta has a small expected error on a future observation z, which is formalized by expectation of L of theta z for some loss function L of your choice. For that task, you have n independent observations, z1, zn, generated from a probability distribution p, and you may want to find a fixed theta which has a small expected error. But you may also want to find a random theta which has a small expected error. In other words, you may want to find a probability distribution rho n on theta which has a small expected error, expectation of theta following rho n, expectation of L of theta z. A PAC-Bayes bound is a bound on the area of rho n which holds with high probability, like this one. Now as you can see, the above involves a probability distribution rho 0 called the prior. This can be any distribution of your choice, but it may not depend on the observations z1, zn. Also, the bound involves the KL or Kullback-Leibler divergence, which measures the distance between the posterior rho n and the prior rho 0. In particular, this term is large if the posterior rho n is very different from the prior rho 0, and it is small when those are similar. That KL term appears in most of the PAC-Bayes bounds because one of the keys to prove those bounds is a change of measure lemma discovered by Donsker and Vereden in the 1970s, where, as you can see, the KL shows its head. But its presence has only rarely been questioned, let alone replaced with a better and tighter measure. Well, that is, until this paper. A better than KL PAC-Bayes bound. The main result of a paper is the following PAC-Bayes bound on the error of the posterior rho n, which holds with probability at least 1 minus 2 epsilon. Now let's comment on a few things. First, the bound holds simultaneously for all n and all posteriors rho n, which depend on the n observations. Now that's really nice to have, although the novelty isn't specifically here. The main novelty is that there is no more square root of KL. Instead, it is replaced by the ZCP divergence, defined by this formula. Now, before opening the champagne, is ZCP actually better than the square root of KL? Because there's no point in replacing the square root of KL by something worse. And indeed, it is better. Precisely, the ZCP is always smaller than the square root of KL times the square root of log of n out of epsilon. That supplemental factor is fairly small compared to the square root of n in the error bound, and hence does not significantly worsen it in the worst possible scenario. In the best scenarios though, ZCP is much smaller than square root of KL, leading to a much better error bound. For example, when P and Q are the following Bernoulli distributions, ZCP remains small while the square root of KL tends to infinity when P becomes close to 0. So ZCP is order-wise smaller than the square root of KL, and the new bound actually improves upon the previous one. There are other improved results of that kind, and if you are interested, I will put the link to that amazing paper in the description. But now, rather than giving an exhaustive list of bounds, I would like to take you on a trip together with me through the proof of the result that we have just seen. Now, don't worry, we won't go through heavy computations. The point here is just to see where the ZCP comes from and how the coin betting mentioned in the beginning of the video comes into play. Proof of the bound. For any theta, let delta I of theta be the ith term of the sum, and delta bar of theta be their sum. We want to bound the error of theta, which follows posterior distribution rho n for any rho n, which is the term on the left of the screen. We first decompose the bound by introducing the prior rho 0. The term II on the screen is further decomposed by using Fenchel-Young's inequality, which we recall here. In our case, the convex conjugate of a function f is defined as the following f star, and therefore for any x and y, xy is always smaller than f of x plus f star of y. Now take the term II, and applying Fenchel-Young to x is equal to delta bar of theta, and y is equal to d of rho n on d of rho 0 of theta minus 1, we obtain the following bound for some function f to be specified later. It only remains now to bound each of the terms I, A, and B, and we're done. First, the term I. Since the prior rho 0 does not depend on the observations, it is a sum of independent random variables, and we can bound it using the following concentration inequality. So I'll skip the details here, this is not the most important point of the proof, but if you want to know more about concentration inequalities, I have made a detailed video whose link will be in the description. For the rest of the proof, we fix f of x is equal to epsilon exponential of x squared divided by 4n. Now we proceed with the term a, for which we will use the coin betting procedure mentioned in the beginning of the video. If you consider the coin betting procedure, such that at every round I, your enemy sets the coin as delta I of theta, then f of delta bar of theta is equal to epsilon exponential of delta bar of theta squared divided by 4n, which is lower than epsilon times the wealth of the best fixed predictor. And this, by definition, can be written as the regret times your own wealth at time n. Now, a good coin betting strategy ensures that the regret is lower than square root of 2n plus 1, and we can bound the term a as follows. Now, the improvement lies in the fact that your wealth wn is easier to bound than the wealth of the optimal predictor, because the optimal predictor depends on all of the observations, while your strategy may only depend on the previous observations. Following this argument, we can prove that the expectation Wn is a non-negative martingale, which is always lower than 1 out of epsilon with large probability by the so-called Wield's inequality. The bound of the remaining term b comes from the choice of f, for which a bound on the convex conjugate is known. Now, beside the computation itself, what is interesting is that it yields the ZCP divergence and the final bound of the theorem. Finally, I would like to insist on the two keys explaining why the ZCP divergence appears rather than the square root of KL. The first key is to decompose the error with Fenchel-Young's inequality. xy is smaller than f of x plus f star of y for the function f of your choice. A mediocre choice of f may give you back Donsker and Varidan's formula with its undesired square root of KL. So the choice of a good f is crucial, taking us to the second key of the proof, the coin betting. Now, the coin betting offers us the function f of x is equal to exponential x squared divided by 4n as a good approximation of the wealth of the best fixed constant predictor, and the convex conjugate of that f yields the ZCP divergence. Alright, if you enjoy videos on fantastic research papers like this one, please let me know in the comments section down below. Also, don't forget to give it a thumbs up, subscribe and hit the bell icon. I would really appreciate that. Thanks again so much for watching. I wish you a wonderful week, and I'll see you in the next video. Cheers.